So last time what we saw was this notion of implicit data structures. These are data structures where all you have is an array containing the input data, and you are allowed to store, at most a constant number of extra storage cells or pointers or numbers. So we saw some implicit data structures, including this biparental heap, and we also proved some sort of a trade-off that if an implicit data structure, all it stores is some partial order on the values in depending on where locations they are in, then the product of the search time versus update time is at least n. Okay. Then at the end of the last lecture, I gave and we can combine both these searches. You don't necessarily have to find the min and then do a search. You can combine them, and in any case, in order log n time, you can find the min or max or find x. All of this you can do in order log n time. But insertions, how much time will insertion take? Order n time, because you can again search to figure out where you want to insert, but then just like in a sorted array, you have to move elements and you end up spending linear time. But there is some operation. Okay, so let me write that now. But if I consider this following operation, where you say replace the smallest if I want to replace the smallest with an element which is larger than the largest, how much time do you need? You can do it in logarithmic time, because so I mean in this case I want to replace the smallest with, let's say, 45 or something. Then I have to spend logarithmic time to find where the smallest is. But once I find that, I just don't have to do any move. Just remove, replace that by the largest. And you still have the rotated list, right? Except the smallest is now moved location, but it's a rotated list. Okay. So this is something you can do in logarithmic time, and this is what I'm going to make use of to design a data structure where this rotated list is going to be a building block. Okay. So consider the following again with the way we started off yesterday with blocks of size root n or blocks, ith block having I elements. Let's do something like that. I will have let's call this as blocks of rotated list. So, you have ith block has I elements in a rotated list, and all elements in block I are less than or equal to elements in block I plus 1. I mean, for simplicity, I can assume that all the elements are distinct. So, I do not have to even say less than or equal to, but the most general definition will say less than or equal to. So, this is what is a structure I am building with rotated list as building blocks. So consider this, right? I have ith block having I elements, and each block is a rotated list, and elements at ith block less than the elements at I plus first block. Right? Does it satisfy that? Now, let's look at the standard dictionary operations. How much time does it take? How do I search? So, in general, I may have the last block with some few elements, not complete, okay, because your n is not the sum of I. So, I will have the last block which is not complete. Okay, questions? Fine. Okay. How do I search for an element here? How much time does it take, and how do I search? Go to the mid block. Okay. Can you find the block where, see, you have elements of one block smaller than the elements of the next block, elements of, so if you look at it in the block wise, they are all in some sort of a sorted order. So, first thing I want to find out is, if the element is there, which block can it be there, and how do I find that? I don't even know which block. I have to find out which block this element can be. Binary search on what? Blocks, meaning, I mean, block is not a value. I mean, binary search on what? You have to give me a set of numbers. So, when you say binary search on blocks, I mean, you are right direction. What? Binary search on? Yeah, I want to know which block it could be, if at all, or which are the blocks it could be. Find the smallest and the largest of each block. Number of blocks, yeah. Okay. So, search in the middle block where? All the elements? And compare with everyone, is it? Oh, find the minimum maximum there in logarithmic time. Yeah, okay. Okay. Small. Okay. How much time will this take? Okay. So, his algorithm, I will come to your algorithm again. So, his algorithm is, I go to the middle block and check whether your element is there, and that you can do in logarithmic time, because you can search in a block in logarithmic time, log of the number of elements in that block. And if it is there, good, you found it. Otherwise, you will know based on the minimum and maximum in that block whether you should look at left or right and go there and search. Okay. First of all, how many blocks are there totally? Root n blocks, order root n blocks are there. Okay. Log n into log n, log square n, right? Log n, because you are searching in every block, you are searching log n, and how many blocks would you search? Log of root n. because that's the number of blocks. So, that is about log square n, right. Okay, what is your algorithm? Yeah. See, I mean, you said binary search on the blocks. That was I just wanted to pin you down. You can just pick any element in every block, because you know they are all in sorted order. Because of this property, I just pick the first element in each block, let's say, right. This is in sorted order, because anything in one block is less than or equal to anything in the other block. So, I do a binary search on the first element of every block, and then it tells me which are the two blocks where it can be, right. So, suppose I am looking for 23 and I do a binary search on these first elements, it tells you it is between 15 and 23. So, it could be in this block or it could be in this block. It cannot be in this block. Well, actually it could be in this block too, because yeah, I mean you figure out some 2 or 3 blocks. So, if let us say if I am looking for 23, 23 could be here, because 15 could be the smallest element, and it could be here. It could also be here, because you know it is a rotated list. So, maybe it starts at 23 and comes back and goes to 34 or something. No, it cannot be, because all elements are bigger than this. So, it cannot be here. So, it can, you know, if at all. So, you identified 2 blocks in one binary search in logarithmic time. You identified 2 blocks where it could be, search in those 2 blocks. So, overall you have logarithmic, not log square n, but log n, right, about 3 log n, 3 log root n, something like that. 1 log n to search on the binary search on the blocks, and then you identify in 2 blocks and search within each of these blocks. Is that clear? Yes. Okay. Now, let us talk about insert. Delete is going to be very similar. Now, I want to insert 23. Yeah, how do I insert 23? So, I find out which block where I should insert. What do I do? No, arbitrary insert. Arbitrary insert element. I mean, I just want to, insert element 23. Yep. All elements or in that block or what? Everything. So, 23 I figure out by doing all these binary searches that it is between these two. So, this is the block where I should insert. So, now insert 23 here, and then what do I do? This block has only take the max element out and okay. So, here I just do whatever moves are required. So, 23 will come here, 27 will come here, and 29 gets bumped out, and what do I do? Yeah, where do I take the max? This is the beauty, right? Take the max element from here, which is 37, and I can place 29 here, right? So, pay attention to the insertions happening in each block. In this block, I am actually inserting it its right position and moving everybody. But in this block, I am not doing a lot of moves. I am exploiting the fact that replace the smallest with the element larger than largest, or the other way. I am replacing the largest with an element smaller than the smallest, right? Both are symmetric. That I can just do it very fast. So then I bump 37 out and place it wherever I should place it here. Okay. Now let's just analyze how much time have we spent. Root n log n. Why? How many moves? Let's say how much moves? Okay, root n log n comparisons. Because in each block you have to find the largest, right? And we know that find the largest in a block takes logarithmic time. There are order root n blocks, so order root n log n time to find the largest. How many moves you do? How many moves in that first block, the worst case? Yeah, and what is the size of a block maximum? In general, maximum root n. So you will move all elements here, that's root n. After that, you are taking the largest and just putting it in one location, right? So 1 in each block. So again root n. So number of moves would be and if you look at it, we have defeated the lower bound, right? Remember what the lower bound was? What was the lower bound result we had? Search into update is at least n, and how much is it here? It's only root n log square n, right? And why? How did we defeat that? Why is that possible? Wake up. I am asking very simple questions. So, we said last time that if an implicit data structure is defined just by partial order on the locations, then search into update time will be at least n. We used it using partial orders, chain, anti-chain, Dilworth's theorem, and use that. And here I am saying here is an implicit data structure where search into update is not at least n, it is only order square root of n times log square n. And why? Because there is no partial order. I can't just say that here is a partial order on the locations, that third element, element in location 3 will be less than or equal to element in location 7, which no, because the rotated list gives a lot of flexibility about where the smallest element can be in that block. Okay. So, I have a certain partial order about element here is less than or equal to element here and so on, but among this there is no partial order. I mean they could come in any order they want, the smallest can be anywhere. Okay. So, the point of this whole thing is to also see the limitations of lower bound results. Okay. Okay. Now, I am going to give you one more implicit data structure where okay. So, here is a structure where search is very fast, but insertions and deletions are like root n log n. I wanted to sort of balance them and bring both of them below root n. Okay. And here is a nice structure which combines whatever the beep what you learned and rotated list. So, I will call that as beep on rotated list. So, recall how the beep was looking like. It was a biparental heap. And this is how it was. Your first level has one element, second level has two elements, and so on. And remember, and you also have the property that any element value is greater than Okay, and this helped us to do insertions, searches, and deletes in order root n time. Right, because its height of the structure is order root n, and pretty much like the way we could insert it into a heap, we insert it into a heap, insert it at the last level, check with its parents and look for violations, and swap, go all the way up to the root in the worst case, and that's how we fix the violations. Search was done by viewing this as upper triangular grid, and you start from the top right and you move as long as you find something larger, and then you go down and you will have order root n search time. Okay. So, now what I am going to do is that replace each node. So, now I am going to have or maintain at node I, at the node in level I, a rotated list on I elements. Okay, so, now each node is going to have a rotated list. Okay, within that it is a rotated list of I elements. Ith level has a rotated list of I elements, and what does this property mean? I am going to replace this as all elements, because at a node you do not have one element, but you have a list of elements. So, all of them are greater than or equal to elements at either of its parents. Okay, so, this is the, so all elements here are greater than or equal to all elements here. Similarly, all elements here are greater than or equal to all elements in these two, because each one now has a rotated list. Okay, that is all the structure. Is that clear? So, I have a biparental heap. Now, instead of value, every node having one value, it is going to have a rotated list of values. Now, again, it shouldn't be hard for you to visualize this whole thing in a single dimensional array, right. So, how many values are here at level 2? 4, right, 2 square. How many values at level 3? 3 square. Okay. So, you can visualize this whole thing in a one dimensional array. First element here, and there are 4 elements in the next block where 2 rotated lists, 9 elements in the next block with 3 rotated lists, with the property that this parent child relationship is satisfied. Okay. So, you can easily have a mapping from this sort of a structure to a one dimensional array. Okay. So, what is the height of this structure now? Cube root of n. Does everyone see that? I mean, order cube root of n. Who does not see this? You do not see it. Okay. So, let us say, let k be the number of levels. Okay. K is the number of levels in the structure. We want to get a bound for k. As always, the kth level may not be completely full, because your number does not add up the way we want it. So, except for that, up to k minus 1 levels, everything is full. So, the number of elements n is greater than or equal to, let us say in kth level it has only one element, maybe 1 plus how many elements are there in nth level? L square. So, that is what it is, right. So, do we have a formula for this? 1 to k minus 1. So, it is 6, right? Right, 1 square to L square. That's what I am using. So, k minus 1 into k to k plus 1. Is this fine? K minus? To k minus 1. Okay. So, from here we have 6 n minus 1 is greater than or equal to k cubed roughly. So, k is at most and that is what is order n power 1 by 3. Okay, so, the number of levels is order n power 1 by 3. Okay. So, now let us just go back and do all our operations. Let us do search and insert, and delete is very similar. Let us do inserts. Very similar to what we did in a heap or what we did in a beep, except now you have to keep in mind that you do not have a single element, you have a rotated list inside, right. So, what do? I want to insert an element. I just go wherever the last block where there is some space, I go and insert it here. Okay. That insertion would involve moving all elements in that block of size at most n to the 1 by 3 order, and I may have violated this property, because this element I inserted could be smaller than some element the parents, yeah, because I want all elements at a node is greater than or equal to elements at either of its parents. So, it is possible the element inserted is smaller than some element in the parent. So, what do? So, you do some swap. What swap do you exactly do? What do you, you take this element, do not insert it here, and take the largest element here, and or whichever the largest out of these parents, bring that down and insert it, and take this element and put it here, okay, and see whether there is some violation up there, and I can continue to fix the violations all the way. So, how much time will we take? Height of the structure times log n, because in each of these blocks you have to go and check, find the largest, right. Each is a rotated list. So, I insert and then take the smallest element, see, okay, am I smaller than both the largest of these parents? No, if I am larger, then I just take the largest of the parent, bring it down, move it there, and then I do the same comparisons upwards. So, I spend about log n time in each level, and total number of levels we argued is order n power 1 by 3. So, that is order all right. Okay. Search is very similar to the way we did it in a beep. Okay, recall how we did the search. I mean, it's useful to view this whole thing as a so you read, think of this as level by level is one block. And the way we did the search is we went, moved all the way, and then we did this kind of a search. Okay. And here you do the same thing, except now in each element of this grid, you don't have a single element, but you have a rotated list. So you go search in that list, okay, and keep following that up. And so I will let you fill up the details to realize this whole thing also takes order n, number of blocks was what we had in the beep. Now there is a logarithmic overhead because you are searching in each rotated list. Okay. So here is a structure where both updates and searches are little of square root of n. Okay. And it's not very hard to see that the whole thing can be done in a single array. You don't, even though we have drawn it like this, you can map it into a single one dimensional array because you are filling it level by level, the number of elements in each level, number of elements in each block, everything is fixed. So you can view the whole thing in a single dimensional array, and you have a way of doing searches and insertions and in this much time. Okay. Okay, so this is not the end of the story on implicit data structures, though I am going to pretty much stop here on this discussion. But you are currently there is a structure where you can do insertions, searches and deletes in order logarithmic time. This was solved only in like late 90s, using no extra space, but in a one dimensional array, but it's very, very complicated. It just encodes the pointers in a very clever way inside the elements itself and so on. Okay. But there is a log square n structure known quite some time back in 80s, and this was improved to log n in late 90s. Okay, so there is such a structure. Anybody interested in exploring can explore, and you may not get this far soon, but at least get to intermediate structures and you may be able to read and understand them. Okay. So what I am going to do in the next half an hour or so is to talk about another interesting trade-off lower bound result, and then again we will beat the lower bound as we have been doing it, by removing the assumptions of that statement. Okay. So people were, so this was a motivation for this question. You can basically we have an intuitive idea that if there is not much structure in the input, then it will be very hard to search. And if there is a lot of structure, it will be easy to search, right? The extreme examples are that if you have an unsorted array, there is no structure there, and how much time you need to search? Linear time, because you pretty much have to check with every element there. The other extreme is that if you have a sorted array, then a lot of structure and you can search in logarithmic time. Okay. So people were wondering, maybe, how do you formalize this notion of structure, right? It's still talking about implicit data structure. One way we did was looking at the partial orders. Okay. See whether that structure satisfies some partial order in the locations. Another way is the number of permutations allowed by the structure, permutations on the input. Okay. So if you have an unsorted array, then how many permutations are allowed? Your input can be in any of the n factorial permutations, because you know there is no structure. So, there are n factorial permutations, and search time we know is linear, you can't do better than this. Okay. The other extreme, you have a sorted array. How many permutations are allowed? How many permutations of the input is allowed? Only one. It has to be in, you know, smallest element, second smallest element, that is it. Only one permutation, and you can search in logarithmic time. What I would like you to check is how many permutations are allowed by an input if the array is in a heap form. Okay. Let us say on 4 elements, let's look at a heap on 4 elements, right. What are all the permutations allowed? And let us say we take the first 4 elements as the values of on the nodes of the heap. So, I could have 1, 2, 3, 4. I could have 1, 3, 2, 4. That is all, right. What else can I have? I mean, what are all the possible heaps I can have on the numbers? So, 1, this is 1, or 1, 3, 2, and 4. Hmm? Okay, sounds right. I mean, if I assume n is the power of 2, let us say it is a complete binary tree. So, what he is saying is that, you know, I have no choice on the first element, it has to be the smallest, right, and then actually not quite, not quite. So, this whole thing is a heap on certain number of elements, you know, n by 2 elements, let us say, and this is another heap on some n by 2 elements, and I have a choice on the second and the third smallest. Second smallest can be here, or second smallest can be here, fine. So, that was your 2, but yeah.
Okay, so my Tn should be greater than or equal to 2 times Tn.
2 times T n minus 1 or n by 2.
Oh, n by 2.
Okay, I will leave that as an exercise to verify, you know, how many permutations are allowed by a heap. More than exactly, yeah. So, there are more choices. Yeah, there are more choices. So, what were you saying?
4 can be there at the right node of 1 because
4 can be there at the right node of 1. Yes, exactly.
and
Yeah, right. Yeah. Oh, so we do have one more choice even here for 4 elements. Good point. No, 1. Okay, 1, 2, 4, 3. Excellent. Yeah. No, that's not possible. 1, 3, 2, 4. That's here. Yeah. Yeah, that's a good point. So okay, it's a nice, interesting exercise for you to think about how many permutations are allowed if your array satisfies a heap order. We also now know what is called a beep order. And we know how much time it takes to search here. How much time? In a heap, order n. We also sort of argued that omega n is required because there can be an anti-chain of n by 2 elements. And similarly here, it's root n. Okay. So, and you can see that there are lots of permutations allowed here and search time is large. Here it is the other extreme, very restricted, the search time is log n. In beep you will have fewer permutations and you have a root n. So, this connection between, is there a connection between the number of permutations allowed and the search time? Okay, so that is a question we want to answer. And so here is a claim and let us see how to prove this. So, let P be the number of permutations obeyed by the given structure array let Sn be the search time on that structure. Then if involves the element being searched for. So, this is interesting. This says that suppose you are okay. So, I tell you here is my array or a structure which the number of allowable permutations of the input is some p. Then any search algorithm on this structure must necessarily take at least p power 1 by n time, under the assumption that every comparison involves the element you are searching for. Okay, so, your search algorithm, what will it do? So, you have this array, what is the search algorithm going to do? I am searching for x. So, it is going to compare x with some location, right. That is what binary search does. It takes x, compares the middle element, depending on the outcome it takes x and compares with some other element, depending on the outcome it takes x with some other element and so on. But in the case of sorted array, there is no point in taking two elements and comparing, right, for the search algorithm. Why not? You already know that, you know the outcome. You take the fourth element and seventh element, you know fourth element is less than or equal to seventh element. Sorted array gives that guarantee. So, any search algorithm which is going to do such a comparison is doing a waste of comparison. Okay. But here it is not necessarily clear that when I am trying to search for an element in this array, it might help to pick two elements in the array and compare. Okay. It might, it maybe not, we do not know. But the point of this theorem is that if every element, every comparison in the search algorithm involves the element you are searching for, then the number of comparisons any search algorithm must do is at least p power 1 by n. Okay. So, we will prove we will actually show that p is less than or equal to s power n. Okay. So, I give this array and I tell you that these are the permutations, or I just tell you the number of permutations, maybe even these are the permutations, and you come up with a search algorithm. What is a search algorithm? It is just a comparison tree, right. How does a search algorithm look like? It is going to take x, let us say A is your array, then it is going to take x with some ai, and then depending on the outcome, if it is equal to, it will stop, if it is less than or greater than, it is going to take x with some other aj, and again depending on the outcome, it is just going to keep. So, that is the search algorithm, and this height of the search tree is what the maximum search time is, right, which we assume it to be at most s. Okay. So, for any element you want to search, there is a search tree. That is what the search algorithm is. It says, oh, you want to search for 35, this is what you should do. You go and search in this location, depending on the answer, you search here, 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 and so on. Okay. Actually, no, the search algorithm does not depend on the element you are looking for. Right. Whatever you want to search for, here is the algorithm you follow, right. How does a binary search tree? It does not say, binary search does not say if you are searching for 35, you should do this, you are searching for 47. The search algorithm is go to the middle element, compare your x with that element, depending on the answer, you go left, go right, and so on and so forth, right. That is what the search algorithm is. And so, I have a search tree, and the question is, let us assume that the height of the search tree is at most s, and I want to argue that the number of permutations allowed by your input is at most s power n. Okay. So, here is how the proof will proceed. Let us see the smallest element where can it be, right. I want to see. So, what is given to you, an array, and it is supposed to satisfy p permutations, and somebody has come up with the best search algorithm for it, which is a search tree. Okay, the tree is given to me. Now, I want to argue the smallest element of the array, what are the possible locations where it can be, okay, looking at the search tree. Okay. So, this is the claim, can be in at most s locations. Okay, and the proof is this: search for, let us call the smallest element of the array, let us say is some a0. Search for an element less than a0. Okay. So, here is a set of permutations given array, and you have a search tree, and I am going to say, okay, in this array a0 is the smallest element. I want to search for some element less than a0 and see how the search algorithm will proceed, right. It is less than the smallest. So, the search algorithm is going to follow this algorithm, it follows the tree, right. I am searching for x, it will compare at some location, some location. So, which path of the tree will it take? the leftmost path, right, because I am searching for something smaller than the smallest. So, whatever location you are going to put in, it is going to just say less than that, less than that, less than that, it is going to follow this path and it is come back and say the element is not there, right. The search will follow the leftmost path of the search tree. Okay. So, now search for A naught. Okay. So, now I am going to say okay, search for the smallest element. Okay. It is going to follow pretty much the same path, right, because every location it is going to see here, it is going to say less than, less than, less than, except may not be the last, except which comparison, x with A naught. Only when x with A naught is seen in this path, it is going to stop and say yes. Everywhere else it is going to say less than, less than, less than, because x A naught is less than everybody else in the array anyway. So, only if it hits, if in this path, in the search path, if it hits the element A naught, it is going to look at it and stop and say yes, A naught is there. Now, it should hit it, right, because if it does not hit it, it is going to follow the same path and say A naught is also not there, which is wrong. We know A naught is the smallest element in the array which is there. So, putting all this together, what am I contributing? What am I saying? A naught must be in the search path of x. Okay. Then A naught or A naught's location must be in the search path. Right. When I am doing some search, it will follow this, and somewhere it is going to hit A naught and it will stop equal to and stop. So, in this path, leftmost path, I must have A naught in one location. Okay. And A naught cannot be anywhere else as well, right, because A naught is the smallest element. So, this location containing A naught cannot be anywhere else in the search tree, because if it is, suppose it is in this. Okay. So, I compare it with this location, and that means that this is smaller and I am hitting this location. That means A naught is larger than this element, but that is not true. A naught is the smallest element. Okay. So, the conclusion is that the number of locations A naught can be is at most s. All the locations in this path are the only possibility for the smallest element to sit. Okay. So, and that was my subclaim. The smallest element of the array can be in at most s locations and cannot be anywhere else in the tree. Any other location. So, this is quite subtle. So, you are given a search tree, and I am going to now I am saying that the smallest element, if this is how your search algorithm is, the smallest element can be in some location in that path, in one path of at most s elements. Okay. So, and that proves this. The smallest element of the array can be in at most s locations. Now, I am going to assume by induction, right, when n equal to 1, I have proved it. What is my claim? I wanted to show that p is at most s power n. If there is only one element, then that is the smallest element, it has s locations. By induction, sorry, not when n is 1, I want to say the smallest element. By induction on n, assume that the first the smallest I elements can follow at most p power I permutations. Then by the same kind of an argument, I am going to show that the next smallest element can have at most s locations where it can be. So, together there will be at most s power I plus 1 locations. Okay, let a I plus 1 be the I plus first element. Pretty much by the same argument, I want to show that this element also can be in at most s locations. Why? Well, search for some x between the ith element and a I plus 1. Okay, so, in my search tree, which is basically like this, I am looking for some x which is between a I and a I plus 1. Okay. If a 1, let us say a 0. Okay, so a I is the I plus first element. Yeah. I am looking for something between a I minus 1 and a I. How does a search proceed? Well, search path follows certain path in the search tree and comes back and says, oh, this element is not there. Okay. Now, I want to go and pay attention to if I want to search for a I. So, in this search path, there are certain locations whose values are higher than a I minus 1, there are those which are minus 1. Okay. Whenever you hit such locations, it is going to follow the same path. Okay. When I am searching for a I, whether does not matter whether I am searching for something between a minus 1 and a I or a I, whenever some element here, my comparison is going to say no, I am bigger, it will follow the right path. Whenever I hit something here, I am going to say I am smaller, I am going to get the left path. So, it will follow exactly the same path except when it hits location a I, at which point x would have said no, I am smaller, whereas when I am searching for a I, it will say yes, I found it, and I will stop and say yes. Okay. So, by the very similar argument what we have is this path should have a I, and a I cannot be anywhere else. So, a I has at most, so a I location of a I must be in that search path. Okay, we are critically using the fact that your search involves the element you are searching for. Okay, your tree is looking like x with some location. Okay, so that means that you have only at most s ways to extend it, and we will have proved the main claim which we wanted. Okay, we want to show this. So, a 0 to a I can follow okay. So, therefore, the total number of permutations is s power n by induction. Okay, so I mean, if you didn't get it completely, just stare at it one more time, just or try some example like heap or sorted array and see what we are trying to argue here. All you are saying is that we want to show that the search time will be pretty large. Now we are doing it in a contrapositive way, saying that suppose this is the search tree and search time is at most s, then the number of allowable permutations is at most s power n. Okay. So this is a critical assumption about this lower bound, and we will come up with an interesting structure where we will have a lot of allowable permutations, but we can still search fast. Okay. This claim says that if the number of permutations is large, if p is large, the search time is large. Okay. So if p is n factorial, then n factorial power 1 by n is omega n. N factorial is like n by e power n. Okay. And if p is like 1, which is this case, it says the search time is at least 1. Okay, fine. It's a very weak lower bound. That's fine. I mean, there's nothing wrong here. It just says the search time is at least 1. It doesn't say much, but we already know log n lower bound for binary search by various other adversary arguments and so on. So now what I'm going to argue is I'm going to come up with the structure where the number of allowable permutations is really large, but you can still search fast. Why? Because I'm going to violate this assumption that every comparison involves the element you are going to search for. Okay. So it's a very nice, cute structure, and again it illustrates limitations of lower bounds. Okay. We talked about implicit data structure, partial order has a certain lower bound. We moved away from it in rotated list, and we saw that we could beat it. And this is another similar phenomenon here. Some of you might have seen this structure in some exercise I might have given, but let's see. So here is my structure. Okay. Consider the following structure. So start from a sorted array. Let us assume all elements are distinct for okay, let me just draw an example here. Sorted array of distinct elements. Keep elements at even positions as they are. Form pairs of elements in odd positions. By pairing one from the first half to the other from the second half. And swap the pairs. Okay, so here is my structure. So what am I saying? I start with the sorted array, keep all elements as they are in the even position. So these are even positions, I don't do anything there. right? Element at 2, 4, okay. Array starts at 1. Element at position 2, 4, 6, 8, I don't touch them. They are as they are. I take an odd position element. So 1 is an odd position. It is paired with some odd position array in the second half. Okay, so 1 is probably paired with 7. And 3 is paired with 5. So n distinct elements and n is even. Okay, I find this disjoint pairs. These pairs are all disjoint, and then I swap the pairs. Okay. So what do I mean by swap the pair? So 21 goes here. No. 69 goes here. What was there? 7. Okay. And 21 comes here and 15. So now I give you a new array, which is 69, 12, 21, 18, 15, 47, 7, 75. So this is not sorted, not a heap or anything. It just has a strange kind of a structure. Okay. Let's count the number of allowable permutations here. It's not very hard to compute. Number of allowable permutations? Anybody? N by 4 factorial. Yeah, that's very good. N by 4 factorial. Why? Let's look at, how do we fix this permutation? Well, based on how the odd positioned elements are swapped. Let's take the first half. How many odd positioned elements are there? N by 4, right? So take any one of them. How many choices it has to be paired with? N by 4, because the first odd position element can be paired with some odd position element in the right half. So I have n by 4 choices there. Once I fix that choice, the next odd positioned element has n by 4 minus 1 choices, and so on. So total number of permutations is n by 4 factor. So you start with a sorted array, and n by 4 factorial permutations is what you can get by doing this operations. So according to this search lower bound, the search time would be, therefore Sn would be n by 4 factorial power 1 by n omega, and this is, you can verify this omega n power 1 by 4, because n by 4 factorial is more like n by 4 power n by 4. Okay. So 1 n cancels, so it's n power 1 by 4. Okay. If every comparison involves the element being searched for. Okay. But you can search for an element here much faster. So how can somebody come up with an idea of how do I search for an element in such an array? You've seen this before. So you can't answer. Let's see if anybody else gets it. How do I search for an element? Yeah. No, I mean it just
First half, I mean, I have n by 4 elements in the first half.
n by 4 odd positioned elements. Yeah.
So I put it in the second half and commute all of them. So f factor in first
See, these pairs are disjoint. It's very important. So I take one element of the odd position in the first half, pair it with some odd position. So I have n by 4 choices to pair this element. Once that pair is fixed, the next guy has only n by 4 minus 1 choices. Okay. So how can you search? Forget about logarithmic time. Just come up with some search algorithm. How do you search? In this array where it's sorted with some perturbations. And how can I search for an element? Yeah.
compare with the binary search of the even element.
Binary search on the even element seems like the first natural step because the even elements are sorted. So I go and do a binary search on the even elements. Yeah.
It's less than the
So if you find the element, you are lucky, you are done. If not, it's going to take to a location between two even positioned elements and say this is where it should be. Now what do you do? Right. So you binary search on even locations and your search tells you that the element you are looking for is not among the even position locations, but it's something in between these two. Okay. Now what do you what do you gather from here? So one thing you know is that if at all the element is there, it's in the other half, right? It's in the other half in the odd positions, if at all there, because even positions you have done your binary search and you checked it's not there. Among the odd positions, since it here and you know that this element was swapped with somebody on the right, if at all it had been there. So it's in the right, that other half odd positions. Okay, but would you be able to know where there? Are you with me so far? So you have a sort of a log n plus n by 4. In the worst case, even you do linear search on that, you have log n plus n by 4. Now the question is, can you actually improve it to logarithmic time? Okay, so your binary search on the even location puts you between these two elements, and if the element you are looking for is in the array, it's in the other half. What else do you know? If where can that be? I mean, what happened? Who is sitting here? So some element is sitting here. Does that give you any information? That's it. Right. So if at all your element was there, it was swapped with this element because we were just doing swaps. That's why you are not doing arbitrary permutation. So if your element x you are searching for, binary search on the event put me here. If x was here, I mean it's not here now, that means x was swapped with whatever is here, if at all x is there, right. So now take this element, whatever is sitting here, and do a binary search on the events. That will tell you the location of this element in the original sorted array. Okay. So it will say, oh, this element, if 25 was sitting here, 25, when you do a binary search, it's going to say, this is where it should have been there. Now I go there and check, is x there? If x is there, then I know it's there, otherwise it's not there, right. Two binary searches. Okay. So you can do it in logarithmic time. And where am I violating that condition there? The second binary search does not involve the element I am searching for. It is picking some other element and doing binary search. So, okay. So, that's the end of it. So, and this question is, I mean, it's not completely settled. What if you remove this? Is there some, I mean, yes, we can, this bound no longer holds is what we found out, but maybe is there some other bound, and is this really tight? Because as we saw, when P is 1, this is not giving you a good bound. Is there a strengthening of this bound? And as far as I know, these questions are open. Okay.